Hi, my name is Tom Svilans, and I am an assistant professor at the Center for IT and Architecture at the Royal Danish Academy. Today I present the paper GluLamb, a toolkit for early-stage modeling of free-form glue-laminated timber structures. This presentation is organized in three parts: the research context and motivations for the work, an overview and description of the constrained GluLamb blank model developed in the work, and finally, three case studies that show how it is used in three different applications: in an architectural practice setting, in a design-to-fabrication workflow, and in a research project that links CT scanning in forestry with freeform timber design. As a brief summary, GluLamb is a software toolkit for design-oriented modeling of freeform timber structures and interfacing with computer-aided engineering and manufacturing domains. By embedding material and process parameters into the model, it offers a type of Glulam materiality to the designer. It is currently exposed as a plugin for McNeil's Rhino and Grasshopper modeling environment, freely available for download and usage. The motivation for GluLamb stems from two key considerations. Firstly, as digital design evolves to accommodate bio-based systems and a deeper material engagement, the idea of digital materiality in digital modeling has gained an important status. New models of digital design practice have therefore come about which connect digital modeling and simulation to material behavior and its consequences. Second, as timber buildings increase in both formal and logistical complexity, methods are needed to identify risk, cost, and potential difficulties early in the design process. Much of the complexity of working with timber is due to its anisotropic properties, and this translates to particular required know-how in the production of timber elements. The GluLamb blank, or the near-net shape of a manufactured GluLamb element, occupies an interesting space between sawn lumber and the finished architectural component. Curved glulams are unique among other engineered wood products, as they are most often tailored for a specific design geometry instead of being manufactured from a stock material form. As such, exposing the constraints and limitations of GluLamb manufacturing within the design process helps to facilitate the successful execution of highly complex timber geometries with many unique elements. In industry, there are three main GluLamb blank types: straight, single curved, and double curved. Straight blanks are the simplest and consist of laminating boards of arbitrary dimensions into rectangular beam-like elements. Single curved blanks are curved in a single plane, and therefore their lamination dimensions are constrained by the degree of curvature. The higher the curvature, the thinner the laminations must be. Double curved blanks are curved out of plane, and therefore impose a further constraint on both lamination dimensions, leading to an exponential increase in laminations. The image on the right shows an example of a double curved blank of moderate curvature, showing how the manufacturing complexity greatly increases with freeform timber elements. There are two implications of this relationship between curvature and the GluLamb blank. As the design geometry becomes increasingly curved, more wood must be processed to achieve the necessary GluLamb blank geometry. This results in a greater percentage of waste. In some cases, only 10 to 15% of the original input material is present in the final manufactured element. Further, as the GluLamb blank increases in complexity, so does its cost increase. On the right is a nominal relationship between the cost of a straight GluLamb blank and the two curved blank types. In the case of a highly double curved blank, the cost can be higher by a factor of 15 compared to a straight blank. These are important considerations that need to be made explicit in early stages of a timber design project. The objectives of GluLamb are therefore as follows. 1. The fast generation of reliable 3D geometry of GluLamb elements. Design models often necessitate remodeling to reach a quality fit for digital production. Having more robust geometry at the outset of a design project can help to ease the translation to the production model. Number 2. The categorization of GluLamb geometry according to the three GluLamb blank types to assess production complexity or manufacturer-specific capabilities. Number 3. The estimation of material specifications such as lamella dimensions based on the GluLamb blank geometry and appropriate manufacturing codes. Number 4. An indication of the alignment of the design geometry with the longitudinal material direction of the wood and its consequences for cutting across the grain. Number 5. An interface for discretizing the GluLamb blank into individual lamellas as well as elements for finite element analysis. And finally, number 6. An interface for building relational models of multiple GluLamb elements and their associated connections. The core model in Glulam is the Glulam class, which has three main inputs: the centerline guide curve, which is a continuous curve without any discontinuities, the cross-section orientation, and the dimensional and material data. This is subclassed into objects which correspond to the three main blank types, so that geometry generation and other functions can be specialized for each type. The cross-section orientation is important for defining the alignment of the GluLamb geometry with a variety of design drivers. There are currently 6 orientation types. 1. The vector orientation aligns the cross-section as closely as possible to a single vector while keeping the cross-section perpendicular to the centerline curve to create a road-like extrusion along the curve. Number 2. The vector list orientation extends this to multiple vectors, where the alignment is smoothly interpolated between defined vectors. 3. The surface orientation locks the alignment of the GluLamb to a freeform surface. This only affects the cross-section orientation, which means that the centerline curve is not constrained to the surface. 4. The rail curve orientation aligns the GluLamb to a secondary guide curve. 5. The planar orientation is similar to the vector orientation in that it aligns the GluLamb to the normal of a defined plane. This is also the default orientation for planar or single curved GluLambs. And finally, number 6. The RMF orientation simply uses the default rotation minimizing frames of the centerline curve to orient the GluLamb cross-section. The specification for lamination dimensions is driven by the relationship between curvature and lamination thickness. This can be defined according to a standard such as Eurocode or APA, or controlled freely. The centerline curves and bounding geometry of individual lamellas can be subsequently extracted for more detailed modeling or analysis at a per lamella level. Glulam offers a couple of basic visualization tools for qualitative analysis of Glulam elements. The fiber orientation analysis maps the longitudinal material direction of the blank onto the design geometry as a color, using the same principle as normal mapping in computer graphics. This allows a fast identification of similar design geometries that are cut from different types of blanks. On the left, the red outline shows a curved blank, and the color gradient across the design element shows the changing material direction. On the right, the red outline shows a straight GluLamb blank, and the constant color indicates an unchanging material direction. The fiber deviation analysis compares the surface normal of the design geometry to the longitudinal material direction. This helps to identify areas of fiber cutting and potential durability issues in the design geometry. On the left, the close alignment of the curved GluLamb blank means that most of its surfaces are aligned with the fiber direction. On the right, the discrepancy between the freeform design element and the straight GluLamb blank manifests as large areas of fiber cutting and end grain. Extending the model from the individual GluLamb to a structure, Glulam offers a structure class, which is a container for multiple GluLamb elements as well as their connections. The connection class holds references to the GluLamb elements it connects, and the element class holds references to one or more connections. This creates a relational model that permits a fast traversal of parts and ensures that connection geometries are synchronized between elements. The first case study is the Magalungen Park Bridge. This is a schematic design for a pedestrian bridge in Stockholm, Sweden, that is developed at White Architecture during a research secondment. The project begins with basic design parameters: the maximum slope of the bridge, the start and end points at different elevations, and the necessary clearances for a train track, a major roadway, and a pedestrian path. The site is 3D scanned to also identify key natural features such as protected trees that need to be avoided. The project creates the opportunity to deploy GluLamb in an early stage design setting within a practice. This allows fast, iterative development of design strategies that embody GluLamb constraints and reveal implications for further stages. A key part of this case study is the rationalization of the GluLamb blank types in the resultant freeform timber design. By modifying the type of GluLamb blank that the design elements are manufactured from, anticipated savings in production complexity and cost are achieved. It is important to note that the design geometry remains unchanged, and only the GluLamb specifications and types are varied. For example, instead of an element using a double curved GluLamb blank, a slightly larger single curved blank can be used as long as it doesn't result in excessive end grain exposure along its surfaces. The top left part of the image shows a design model with primarily double curved blanks in red. The bottom right corner shows how these are replaced with a combination of yellow single curved blanks and blue straight blanks by relaxing the tolerance between the design geometry and the GluLamb blank type. The M-Bridge demonstrator is a design based off of the previous case study, although with a more complex freeform geometry. GluLam is here used to model the individual elements as well as more complex multi-element subassemblies for the legs. GluLam is also used to map material specifications and evaluate manufacturability of the elements. The structure class is used to move from a schematic design model to a discretized production model informed by manufacturing constraints, while retaining the relationships between elements. Long, freeform beams are segmented into shorter pieces, which are grouped, while connections between the beams are reallocated to the appropriate segments. Splice connections between the segments within a long beam are also added. The relational model therefore allows tracking connections between elements. This also permits a small number of connection details to be programmed, which are then parametrically variated according to the specific geometries of each unique pair of elements, as on the right. GluLam is therefore used to create material specifications that inform the material sourcing and laminating of the blanks, to limit the beam segments to the specific machining limits, and to generate machining geometry for each individual piece. The final case study shows how GluLam is used within a CT scan-driven fabrication workflow between a sawn log and a GluLam assembly. Here, a series of logs is CT scanned and a map of particular material qualities is defined. This allows a mapping of specific qualities on a per lamella basis to precisely place specific parts of the log onto specific parts of the final designed element, according to design performance demands. GluLam is used to decompose the design structure into individual GluLam elements and further into individual lamellas. These lamellas are then mapped onto specific areas of the logs to align the found material qualities with the design intent. The image on the top left shows the mapping of the design performance demands onto each individual lamella in the structure. The image on the right shows the allocation of lamellas onto specific boards cut from the logs. GluLam is used to facilitate the data management between the sawn log on the top left, lamella dimensions and identification on the bottom left, pressing parameters on the top right, and the final robotic machining of connection details on the bottom right. This allows the workflow from log to finished structure to remain flexible and robust, even with small design changes just before fabrication. The left image shows the complete structure. The top right shows some of the machine connection details between elements, and the bottom right shows a pre-assembled component with all prefabricated connection details derived directly from the GluLam model. In conclusion, GluLam is a toolkit that aims to augment the digital design model with GluLam-specific parameters and constraints, and thus embed a type of GluLam materiality into early-stage design processes. The key offering is an integration of material and fabrication concerns into early and fluid design stages that help to highlight downstream risk and complexity. The future ambition of this work is to continue to systematize key aspects of freeform GluLam design and production in order to mitigate some of the risk and complexity present in the development and construction of complex timber structures. Lowering these barriers would allow the design space of freeform timber structures to be explored more easily, fluidly, and ultimately more imaginatively. The development of GluLamb began during a PhD project at the Royal Danish Academy within the EU-funded in-a-chain research network. The case studies have been developed in collaboration with partners White Architecture, Bloomer Lehman, Microtech, and Umeå University. Thank you very much for your attention.